We closed the last podcast classifying what we called computable functions. Does that mean there are non-computable functions? Let's see. You may remember a Star Trek episode where an android blew smoke out of his ears by trying to understand somebody saying, "I am lying." Well, if he were lying, then he would actually be telling the truth. But if he were telling the truth, then he would be lying. Think about that long enough and smoke may come out of your ears. Or try this one. Does the cook cook for himself? Well, no, he doesn't, because he cooks for everyone who doesn't cook for themselves. But if he doesn't cook for himself, then he must be cooking for himself because he's one of the people that doesn't cook for themselves. Smoke? How about two sentences in a row? Well, if the previous sentence was true, then this sentence must be false. But that means the previous sentence wasn't true. There's definitely smoke appearing somewhere. Or if we take it mathematically, we could ask, does the set of all sets contain itself? Well, if it contains itself, then it must not be the set of all sets because it's a set containing itself. But if it doesn't contain itself, then it doesn't contain the set of all sets. Smoke coming out of the ears. All of these boil down to something that's called a language paradox, probably the language paradox, which boils down to, if it does, then it doesn't, but if it doesn't, it does. Are we confused yet? And what does this possibly have to do with computers? Well, let's ask a question of this simple program. Does it ever stop? Well, the answer depends, of course, on what x is. If x is 0, then it stops. If x is not 0, and assuming we're not dealing with negative numbers here, it's going to go on forever. Now, I'm going to ask you to get kind of kinky here. Take a program and feed the program to itself. Think of it as a C compiler, which is compiling the C compiler. If we did that, and the program halts, we call the program self-terminating. I ate myself, and I terminated. If it doesn't stop, then it's not self-terminating. It's just definitions here. We're not trying to understand anything yet. The key idea is, can I feed a program itself as input? And since every program we know is nothing but ones and zeros, and every program just takes as input ones and zeros, we can certainly feed that set of ones and zeros that corresponds to the program to itself. So, if I take the program we just looked at and feed it to itself, does it stop? Well, assuming that the program itself isn't all zeros, and if it's got enough stuff in it, it probably isn't there, then it's not 0. So if you feed it itself, it doesn't stop, and it's not self-terminating by our definition of what self-terminating means. If this is sounding confusing, you may want to stop and rewind and go back to where we defined self-terminating. Now I've made a small change to the program. Does it stop if it's fed itself? Well, again, assuming that it isn't all zeros, yes, it does indeed stop. So this would be a self-terminating program. Clear on the concept? Let's go on. So here's a question. Can we write a program that will determine if any program is self-terminating or not? Okay, so we're going to write a program, we're going to feed it another program, and it's going to say yes or no. The program is self-terminating, the program isn't self-terminating. So we take any program in pink, and we feed it to our fancy determine if it's a self-terminating program. Now it's my program, so I can make it work however I want. And I'm going to define that if it has determined that the program in pink is a self-terminating program, it's going to set a value of x equal to 1. Yes, it is a self-terminating program. And if it's not a self-terminating program, that program in pink, it's going to set its value of x to 0. And now this is what I'm going to call my real determine if it's a self-terminating program. Now, I'm going to make a small modification to my program. I'm allowed to make any changes I want to my program. And right at the end of the program, I'm going to put our little code snippet from before. While x is not equal to 0, x is equal to x plus 1, stop. Which means that if it's determined that that program in pink is indeed a self-terminating program, then this program's not going to terminate. If it did determine that that program in pink was not a self-terminating program, then this one will terminate. Just follow the x's. And now the coup de grace. We feed it itself. Clear? Let's walk through what happens. If our program is self-terminating, then it will set x equal to 1, and then it will loop forever. So it's not self-terminating. If it is self-terminating, it's not. If it's not self-terminating, which might not be, x will be 0, and so it will terminate. So if it is self-terminating, it's not, and if it's not, it is. Exactly what we saw before. The conclusion we reach is not only does smoke come out of your ears when you think about this too long, but that program is impossible to write. You can't write a program that determines if the input is self-terminating or not, because it wouldn't work for this particular program. This is referred to in the computer biz as the halting problem. And when somebody tells you that the thing you've just proposed reduces to the halting problem, it's another way of saying you can't do that. It's impossible. And unlike those NP-complete algorithms, we have a pretty convincing mathematical proof from a guy named Alan Turing that it is indeed impossible to create such a program. So, we have computable problems, some of which are really, really difficult, and then we have the problems that we cannot compute.